Hello everyone. Welcome to a journey into the heart of classical physics. Every time you use your smartphone, connect to Wi-Fi, or even just look at a sunrise, you are witnessing the power of four elegant equations. These are Maxwell's equations. Before James Clerk Maxwell, electricity and magnetism were seen as separate forces. But Maxwell realized they are two sides of the same coin, woven together to create electromagnetic waves that travel at the speed of light. Today, we are going to dive deep into the math and the physical intuition that changed the world forever. Let us start with Gauss's law for electricity. Physically, this tells us that electric charges are the sources and sinks of the electric field. Look at the differential form. The divergence of the electric field, E, equals the charge density ρ divided by epsilon naught. If you have a positive charge, the field lines spread outward. That is a positive divergence. If you have a negative charge, the lines converge. That is a negative divergence. It is a simple relationship between the field and the stuff that creates it. Now, contrast that with Gauss's law for magnetism. The divergence of the magnetic field, B, is always zero. This is a profound statement. It means there are no magnetic charges, no magnetic monopoles. If you take a magnet and break it in half, you do not get a north pole and a south pole. You get two smaller magnets, each with its own north and south. Magnetic field lines never start or end. They always form closed loops. What goes into a volume must come out. Next, we have Faraday's law. This is where things get dynamic. It tells us that a changing magnetic field creates an electric field. Specifically, the curl of E equals the negative time derivative of B. Imagine a magnetic field passing through a wire loop. If you change the strength of that field, an electric field begins to circulate around it. This is the foundation of every electric generator on the planet. But notice the minus sign. That is Lenz's law, telling us the induced field opposes the change. A quick warning here. This induced electric field is different from the one created by static charges. The field from a charge is conservative. You can define a potential or voltage for it. But this induced field, it has a non-zero curl. It forms closed loops. This means it is non-conservative. You cannot define a unique potential function for it because the work done moving a charge depends on the path you take. Keep that distinction in mind. It is a common trap for students. Does this only happen in wires? Absolutely not. Faraday's law applies to empty space, too. If a magnetic field changes in the middle of a vacuum, an electric field is still created right there. No circuit required. This is the first hint that these fields can exist independently of matter. They can sustain each other. But we are missing one piece of the puzzle to see how. Let us look at Ampere's law. Ampere's original law said that magnetic fields are created by electric currents. But Maxwell noticed a massive problem. Imagine charging a capacitor. Current flows through the wire, creating a magnetic field. But inside the gap between the capacitor plates, there is no current. If you use Ampere's law there, it says the magnetic field should be zero. But experiment shows the magnetic field is definitely there. This paradox meant the law was incomplete. Something was acting like a current in that empty gap. Maxwell's brilliant solution was the displacement current. He realized that a changing electric field also creates a magnetic field. As the capacitor charges, the electric field between the plates grows. That changing field, the time derivative of E, acts just like a real current. So he added a second term to Ampere's law. Now, the curl of B equals mu naught times the current density plus mu naught epsilon naught times the changing electric field. This restored symmetry. Changing B creates E, and changing E creates B. The circle was complete. Let us pause and look at our complete set. We have Gauss's law for electricity, Gauss's law for magnetism, Faraday's law, and the Ampere-Maxwell law. Which of these are dynamic? Only the last two involve time derivatives. They describe how fields change and interact over time. This symmetry is the key. If you have a changing electric field, it makes a magnetic field, which, if it changes, makes an electric field, and so on. Can you see it yet? They are leapfrogging through space. Now for the breakthrough. Maxwell took these equations into free space, where there are no charges and no currents. He took the curl of Faraday's law. Math-wise, that is the curl of E. Using a vector identity, this expands into the gradient of the divergence of E minus the Laplacian of E. But wait, in free space, the divergence of E is zero, so that first term just vanishes. We are left with just the negative Laplacian of the electric field. On the other side of the equals sign, we substitute the Ampere-Maxwell law. Remember, the curl of B in a vacuum is just mu naught epsilon naught times the time derivative of E. When we put it all together, the negatives cancel out, and we get this. The Laplacian of E equals mu naught epsilon naught times the second time derivative of E. If you have studied wave mechanics, your heart should be racing right now. This is the classic wave equation. It describes a disturbance that travels through space. But how fast does this wave travel? In the wave equation, the coefficient in front of the time derivative is 1 divided by the velocity squared. That means the speed, c, equals 1 divided by the square root of mu naught times epsilon naught. When Maxwell plugged in the measured values for these constants, mu naught for magnetism and epsilon naught for electricity, he got approximately 300 million meters per second. He realized this was exactly the measured speed of light. In that moment, he unified electricity, magnetism, and optics into one single theory. So, what does this wave actually look like? It is a transverse wave. The electric field oscillates in one direction, let us say up and down. The magnetic field oscillates perpendicular to it, left and right. Both are perpendicular to the direction the wave is traveling. Notice they are in phase. They reach their peaks and troughs at the same time. This 3D dance of energy carries momentum and power through the vacuum of space. We call the direction of energy flow the Poynting vector, which is the cross product of E and B. One big misconception people had back then was that these waves needed a medium to travel through, like sound needs air. They called it the luminiferous ether. But Maxwell's equations showed something different. The waves are self-sustaining. The changing E field creates the B field, and that changing B field creates the next E field. They pull themselves up by their own bootstraps. This is why light can travel from distant stars through the empty void of space to reach your eyes. No ether required. From the Wi-Fi in your home to the X-rays in a hospital, Maxwell's 4 equations govern it all. They are a testament to the power of mathematical symmetry and physical intuition. I hope this deep dive helped you see the beauty behind the symbols. If you want to explore more advanced physics and master these concepts, make sure to subscribe to Fluent.help. We have plenty more in-depth sessions coming your way. Keep questioning, keep calculating, and I will see you in the next lesson.